my dear friends, welcome to IMS Academy. I am Sourav Upadhyay and I hope that you are good, your preparation is going right on track and everyone is ready, and with full mind and fresh mind we can start our journey towards GATE 2025. And today is the first day where we are kick-starting the fundamental series. Now what is a fundamental series? Let me quickly give you an overview. In fundamental series, a faculty is going to take a certain amount of sessions. It may be 10, it may be 20 or something. And in that sessions, he will be dealing with the fundamentals of the subject. Yes, fundamentals of the subject. Generally, if it's a month of around October, November or December, we will be coming with GATE Score Booster series where we will be talking about different types of questions, different types of approaches and how to quickly get the answer. But now the requirement is completely different. The requirement is to build a very strong fundamental so that on top of which you can build your you can build your concepts. So these series which I am starting today, and it is going to for the next 10 days continuously you will be having the series. Here I am going to talk about the fundamentals of the subject, and I have come up with the fundamentals. So today I am going to start with the fundamentals of a very fundamental subject, which is strength of materials. Yes, SOM. SOM is a very important subject, my dear friends, and not only that, apart from being fundamental, it is also very high scoring. If you ask me about the weightage of the subject, it is about 6 to 8 marks on an average. That being said, it may vary. So let's start, my dear friends, without wasting any time. We are going to quickly start with the fundamentals of the subject, and today what we are going to do, today we are going to see the concept of stress. Today we are going to see how the formula sigma is equal to P by A has is developed, and apart from that, not only that, you will be getting to know so many other fundamentals which will be very instrumental in developing your concepts deep in this subject, right? And let me tell you, my dear friends, don't get mistaken that this is only fundamental and we know the fundamentals, so it is not going to be relevant for your GATE examination. Let me tell you, the clearer your fundamentals are, the easily or very confidently you will be solving the questions also. So everything, whatever we are doing over here or whatever we will do, it will be keeping with respect to the requirements of the examination, right? So my dear friends, let's quickly start this subject. Now my dear friends, if I ask you what do we learn in strength of materials? Now in strength of materials, you will apply, or there is some external force, and that external force gives rise to some internal disturbances, which is commonly known as stress. So first there is the strain takes place, the deformation takes place, and as a result of that some internal disturbances takes place and develops, which is known as stress. So basically in strength of material we will be learning about the concepts of stress, strain when it is subjected to external loads. So whatever structures you are seeing, there will be external loadings, and that gives rise to internal disturbances, and those disturbances are nothing but we deal with in the form of stress and strain. And today the topic is stress, right? So after the session you can download the PPT also, I will be making it available. So important definitions I have already written. So mechanics of material deals with internal effects, that is stress and strain of a body when subjected to external loadings. Now my dear friends, this image that you are seeing on your screen, it will very clearly give you an idea about what are the different types of loading that is possible. So see my dear friends, the different types of loadings, primarily the different types of external loadings that you will be seeing is surface forces, surface forces, surface forces, surface forces and body forces. These are the two external loadings that is possible. Now body force may weight will come, and generally this weight is very small when compared to the surface forces. That is why what we do, we neglect these weights. So whenever in future in SOM, when you are drawing the SFD, BMD or determining the reactions, you don't generally consider the weights. Why? Because you have already neglected. Now next comes the surface forces. What is surface forces? Surface force develops as a result of contacts. Whenever there is contact, surface forces will take place or will develop. So you know that in structures there might be some contacts, and due to those contacts surface forces will be developed. Now when the surface forces or forces have been developed in a region, and let's assume that there is a very big body, it has got a very big area, and above that only small area is being subjected to surface forces. So what we can do, we can assume it to be acting on a very small area, and that is only known as concentrated force. So in the future what you will see that there is a some beam is there, some and here you will be seeing the application of a concentrated forces. So this is the concentrated forces that we are talking about. Next, when the surface force will act on a certain area or over a certain length, that is known as linear distributed load, that you study about UDL, uniformly distributed load, UVL, uniformly varying load, right? So two types of surface forces: concentrated force, when a load is acting on a very small area as compared to the entire body, and then the linearly distributed load, which when the load is acting on some length, some across the length it is there. For example, when you are walking on the ground, so the ground exerts force on your feet, so your feet is having an area which is very very small as compared to the area of the ground. So in that case I can say that it is the case of concentrated force. Similarly, railways, rail wheels, when they they move along the ground, so that means it is a case of concentrated force, that ground is applying on the surface of the wheel. Now my dear friends, what is linearly distributed load? I will give you an example. That suppose that this is the bar and the loadings is something like this. The loading is something like this. The loading is something like this, right? So over here the loading is acting on a certain length. So this is the case of UDL, that is uniformly distributed load. And let's say it is W. So you know that this W is expressed in form of intensity, that is per unit length it is expressed. And if I have to find the entire force, if I have to find the total force, what I have to do? Now I have to find the area of this diagram. Whatever way it is acting, the UDL is acting, I have to find the area. So what is the area? The height is W, and just a minute. The height is W and the length is L. So what is the area? Area is W into L. Very good. Now you will be wondering that where this force is acting. So this force acts through the centroid of this, or the geometric area of this figure. So for example, this is a rectangle. So where will be the centroid or the geometric area or geometric, the center will lie? So it will lie exactly in the something over here in the middle. So if you ask me that, sir, where this is acting, so this will act over here. This will act over here. That is exactly at the the centroid of the figure. Okay. Ram, classes durations will be 4 to 5. The classes durations will be 4 to 5. Okay, 4 to 5. Okay. So this is the way concentrated loads needs to be dealt with. Now I am giving you another example. So for example, let's say there is a concentrated load in the form of the triangle. There is a concentrated load in the form of a triangle. So let's say this is the maximum intensity is W and the length is L. So if I ask you what is the total load, So total load will be just the area of this figure. So what is the total load? The total load is area of this figure, and that is nothing but half into W into L, that is WL by 2. And if I ask you where this will act, so this will act exactly at the centroid. So centroid is over here and it is at a distance of L by 3 from the left hand. So if you have to remove this entire figure and if you have to show the equivalent diagram, so you will show at a distance of L by 3 a force acting something like this, and what will be its magnitude? Its magnitude will be WL by 2. Is it clear? So this is the case of concentrated loadings. This is the case of not concentrated, distributed loading, linearly distributed, yes, this is very important, linearly distributed load. So what did we learn? We learned that the external forces, initially what will happen? External forces will act. They are of two types, body forces and surface forces. Body forces we generally neglect in our discussions. What we take into account? Only the surface forces. Surface forces may be concentrated, for surface forces may be linearly distributed. This we have learnt, and something about linearly distributed load. Okay. Now my dear friends, whatever will be the structure, it will be supported on something. There will be supports definitely. So what is the job of a support? It will restrain your body. It will not allow any movement in the body. And whenever it is resisting something, that means definitely some force it is applying. That is why at the supports there will be reactions, because with the help of that only it is resisting the movement of the body, right? Now for example, consider over here that this structure is resting on a roller. So tell me one thing, the roller is only preventing its downward motion, that is motion in the y direction. So that means definitely it must have been applying force in the y direction. So when I remove the roller, I have to show with the help of a force F. X direction, the body is free to move. That's why I am not showing any reaction in the X direction. If you look at the external pin, or hinge, so what happens? This hinge or external pin is not allowing the body to do movement in the X direction and to do movement in the Y direction. That is why when you remove this, you have to show that okay, there is a force in the Y direction. That means movement is being restrained or constrained in the Y direction as well as in the X direction. That is why two reactions are there. But it is free to rotate. About hinge, I can rotate the body. That means no constraint is there. But when I talk about the fixed support over here, the body is neither doing movement in the X direction, neither doing movement in the Y direction, and neither there is any movement It is not free to rotate. That is why when I remove the fixed support, I have to replace by Fx, I have to replace by Fy, and also I have to show that okay, moment reaction is also there. Why? Because movement is restraint. So there will be support reactions. This is what we have learnt. Now my dear friends, it is very important to know the equations of equilibrium, more precisely the statics equilibrium, because body is at rest and equilibrium equations will always help you in determining the support reactions. How will you know the support reactions? With the help of equilibrium. Now what is equilibrium? When I talk about equations of equilibrium, that means translation equilibrium must be there and moment equilibrium is also unnecessary. For example, at a point if I have to write equilibrium equations, that means I have to do the net summation of forces to be 0 and I also have to do the net summation of moments to be 0. No moment, unbalanced moment should be there, no unbalanced force should be there. Only two equations you have to know as far as the equilibriums are concerned. But you must be seeing this, I have not written any direction. I have not written summation Fx, I have not written summation Fy, I have not written summation about x-axis or y-axis. That means I have written this for all the directions. I have written this considering all that there is a 3D Cartesian system and all those things. That means this is I have written in the form of vectors, and if I have to replace it in the form of scalars, so what I will do? I will write equivalent. What will be the equivalent equations? That means in all the directions if I have to write, I will write summation Fx is equal to 0, then summation Fy is equal to 0, then summation Fz is equal to 0. This is the force. Moment, what will be moment? Summation moment along x-axis will be 0. In y direction there should be no moment, and in z direction should be no moment. Along all the direction there should be no moment. But this I have written for the body when forces are acting in all the directions. But generally what happens? Generally we talk about coplanar systems. Generally we talk about coplanar systems. Coplanar system or coplanar forces. So what happens in coplanar? That means all the forces are acting on a single plane, and whenever it is acting on the single plane, that means only I will be considering summation Fx equal to 0, only I will be considering summation Fy equal to 0, and the moment in direction of z will be 0, because moment direction is perpendicular to the plane, right? So when you talk about coplanar forces or coplanar system, which will be the cases, which is the case generally 99%, you will be dealing with problems in the coplanar system. So only 3 equations of equilibrium are there, rest 3 is not needed, right? Now for doing equilibrium of forces, what is this equation saying actually? Summation of all the forces must be 0. Summation of all the forces. Now how will you know all the forces? Before applying equilibrium, you should know all the forces. How do you know all the forces which are acting on a body? So you draw FBD for that purpose. So for knowing or for applying this equilibrium equations, I must know or I must be able to draw the FBD of the body, that is the free body diagram, which you have been doing since class 12. So FBD is needed, FBD is needed. Okay? So my dear friends, see what I have taken a very general section, I have taken a body, and over here I have been applying forces in all the random directions. But you will see that I am applying force in the external. All these forces are external in nature. But tell me one thing, just I have given the introduction of the SOM subject in this way, that it is the study of internal effects. Internal. You have to study the body internally. So for that purpose, what I do, I have taken a plane and I have intersected the body, because I want to study about the forces which are developed internally. So I have taken a section, I have cut this section. Upper one I will be removing, and I will be studying about the forces which is over here. Now you can see that the upper body has been cut and over here some forces are there. Now my dear friends, see one thing, I don't know that what are the different types of forces which is acting on the body. But what have I done? I have taken one single force which is acting at O, and I have taken one single moment, that is the net moment, which is acting on this O. I am assuming that there is one force, net force, and I am assuming that there is a net moment which is acting at point O. Generally this point O, where you are studying these forces and moments, this is the centroid. Generally, and for the the next, some cases, 99% or you can say everywhere, we will study at the centroid only for a matter of a convenience. You are concerned only about the centroid. Now what I will do, this is the force. Now if you ask me, sir, in which direction this force is there, I will say, sir, in any general direction. It is acting at a space. In space I have taken this f of r. It is in space, not any general x, y, z direction. But if I generally, what do? We, for our convenience, we separate the forces, or we take the components of the forces in x, y and z directions, because that is very convenient for me to analyze. Equilibrium equations are there for x direction, for y direction, for z direction. So for that matter of fact, I can take the components in x, y, z direction. But what I will do, I will do one thing over here. Here, as of now, I will not take in x, y and z direction. Rather I can say I will take one reference, that is this area. This area I will take into consideration, this planar area I will take into consideration, and one component I will take about the force acting on the plane of the area, and one component acting on the normal direction to the area. And similarly, for this moment, one component I will be taking along the plane, moment which is lying on the plane of the area, and moment which is lying perpendicular to area. Force में one force which is lying in the plane of the area, and another force which is lying perpendicular to area. So how many components right now we are studying? 4. 2 forces perpendicular to area, plane in lying in the plane of area, moment, one perpendicular to the area and lying on the plane of the area. And this will give you result to 4 different types of internal loadings that we study in strength of materials. The one which is there in the normal direction to the area, that is known as normal force. The one which is lying in the plane of the area, that is known as shear force. The one which is lying, the moment which is whose axis is passing, who's there on the plane of the area, and it feels like bending the body, that is known as bending moment. And the one moment which is whose axis is there normal to the area, that is known as torsional moment. That is why in the entire strength of materials we study about normal load, normal stress, shear stress, torsional shear stress, torsion you study, and bending you study. So this is how You know, the 4 different forces over here is giving rise to 4 different chapters in your strength of materials. And how it is coming, I have only tried to show over here. So, if I talk about what are the 4 different types of internal loadings that we study, so what is the normal force? So clearly you have to remember only this thing, that is the push or pull effect normal to the area. What is shear force? The force which is acting in the plane of the area. What is torsion? Twisting effect. But about which axis? About the axis which is lying normal to area. And what is bending? Bending, that means taking place, the moment, bending effect. But about which axis? Whenever there is movement, there will be axis. About some axis only a body will rotate. So axis lying in the plane of the area. Generally, in coplanar systems, your torsion will not come into picture. Only normal shear force and bending will come into picture. Generally, when we talk about coplanar system. But we know that internal loadings are of 4 types. Okay. So I hope that this picture that you are seeing over here is giving you a very clear idea that on this plane where is this normal force is acting, shear force is acting, bending moment is acting and torsional moment is acting, right? And here also I have given one some important keywords that okay, this is this, this is this, this is this, this is this. Okay. Now my dear friends, see one thing, what did I do? Same figure, this is the same figure that I am talking about. In this figure, what I have done, I have taken a very small plane. I hope that this figure is clear to you. I have taken a very small area, very small, that means infinite, minuscule, whatever you know, that area I have taken del A. And over here, I am trying to study that what are the different types of force. Now this from here, the lecture becomes very important because this will give you a very good idea that how the stress concept is coming into picture. So over here, this force is being applied, and I have taken del F, okay, I have taken del F. Right now we are talking about concepts, formulas will automatically come, just have patience, everything will come, just have patience. So this is the small plane and on this plane I have taken the force, that is del F. But you know that just for our convenience I can separate these forces in all the directions. So over here in the image that you are seeing, you can see that I have taken one in the z direction, one in the y direction and one in the x direction. Now if you are getting confused about the coordinate system, it is something like this, that this is your x direction, this is your y direction and this is your z direction. So clearly you can see that the area, now this direction is z, this is y and this is x. And this area is something like this, the plane area that I am talking about, this small area is something like this, right. Now, if you keep reducing the area, if it's very small, so the forces which are acting on that area will also get small, that is, there is no doubt. But the ratio of del F by del A, when del A tends to 0, just a minute, the ratio of del F by del A, when del F by del A, when del A tends to 0, is nothing but this coefficient, this ratio is nothing but called the stress. This is nothing but the stress. So what is the stress? Stress is the intensity of internal force. Okay. Intensity of internal force. Intensity of internal force which is acting on a specific plane. Please see, any doubt is there till now? Please check, any doubt is there till now? Please check. Is it clear? Okay. So this is nothing but the stress. This is nothing but the stress. So clearly you can see, my dear friends, over here you can see that I have taken force in the z direction, there is force in the y direction, and there is a force in the x direction. Now see one thing, this is the area, this is the small area, okay, and over here this Fz is acting normal to the area. So the force which is acting normal to the area will give rise to what? Normal stress. Okay, what is normal stress? When the stress is there, or when the force is acting normal to the area, that is giving rise to normal stress. But see my dear friends, this Fx and Fy, del Fx and del Fy is acting on the plane of the area. That is not normal stress. It is acting on the plane, and just now we have studied that whatever force acts on the plane, that gives rise to shear stress. So I think this figure will be very clear to you that this is the plane, as you can see, and the force which is, or the stress which is there normal to this area, that is the normal stress. This is the normal stress. This is the normal stress, and the force which is there on the plane of the area, that is nothing but the shear stress. Okay. Now my dear friends, this small segment that I have taken, I have taken on this figure. Okay, I hope this figure is clear to you. This is small, very small area that I have taken, I have taken over this figure. And then I am analyzing that, okay, when I have cut that figure, there is sigma z and there is tau zy. Now what is tau zy? I have written here tau zy. So this only means that I am referring the plane as z plane. That means what is z? Z here is referring to the orientation, that when I say z equal to 3, so z equal to 3 means what? It is talking about a plane that is lying at a distance of 3 units from the xy plane. And what is y? Y is the direction. That means orientation is z. This plane, the axis perpendicular to this plane is z. So that's why z is written. And what is y? Y is the direction. So zy. What is tau zx? What is tau zx? Tau zx means the orientation of the plane is such that this z, the first z, is denoting the orientation of the plane, that the axis which is perpendicular to the plane is z axis. Okay, so z, and what is x? X is the direction in which the force is acting. So you can see that over here it is acting in the x direction, so zx. So I hope that the orientation is clear to you. Okay. Now my dear friends, tell me one thing. The method in which I can cut a section, it can be like this also. You can cut a section in this way also. So here also one plane is possible, a small plane is possible, the one I have highlighted, and this is what I am trying to show over here, this plane. So in this plane, whatever will, if I have to talk about the normal force, so normal direction is y over here. Yes or no? This is the coordinate system that we are referring as when I am explaining to you. So this is Z, this is Y, and this is X. So clearly you can see that this is the Y, so normal stress will be sigma Y, and in the plane, I hope this picture is clear to you. So in the plane, so I've told you that orientation of the plane is such that Y is perpendicular, so sigma tau Y, and X is denoting what? X is denoting the direction. That means in X direction this shear stress is referring. And similarly tau YZ is also there. And not only this, if I have to cut the plane in this way, that means I hope this is clear, the manner in which I have cut. If I am cutting the plane in this way, so there can be an element over here also. Now I am considering the element on this face. So earlier I have considered the moment on the top face, then I have considered the surface on this lateral face, and then I am considering one plane in the back face, and on the back face, that means the direction will be sigma x, and on the plane there will be in one shear stress will be there in the y direction, one shear stress will be there in the z direction. That means till now what I have shown you, I have shown you that one body is there. This body I have cut or dissected in three different ways, such that one way I have taken, first I have taken on this surface only, so perpendicular to that is sigma z, so that means sigma z came into picture. Then I dissected the plane in this way, that is the lateral way, so the perpendicular direction was y and sigma y is coming. And then I dissected, on the plane in two directions shear stress will be there. In two directions, two shear stress will be there. And finally, I dissected the plane in this way, so such that the normal stress is in x direction, and on that plane, in two different directions, two shear stress will be there. That means whatever small area I am taking, normal to it will be normal stress, and on the plane it will be two shear stresses. So the thing is that why am I trying to analyze this separately? Let us cut one simple cube such that all these three faces will be there on a single cube, and you need not analyze this individually. The benefit will be what? That you can identify or you can analyze all in a single, with a single figure or a single orientation, it will be clear. So three planes, three types I have cut, three surfaces I have taken, all that, so three normal stresses and two shear stresses. So total kitne stress हुए? Three normal stresses and six shear stresses. And now I am going to cut a figure, I am going to cut a cube in such a way such that now I have something like this. Now I have something like this. So now I hope you are able to see the axis. I hope you are able to see the axis. So this is x direction, this is y direction, and this is z direction. So whatever three separate figures I have explained you, that I am showing you over here. And all the shear stresses and normal stresses, whatever I have showed over you, I have showed over here. And this is the general state of a stress. And this is very, very important, my dear friends, in understanding the concept of stress tensor, stress, the symmetricity of a stress matrix, stress transformation, more, all these things. And just I have tried to explain you that how this general state of stress is coming into picture. So how many normal stresses are there? Three normal stresses. How many shear stresses are there? Six shear stresses. On one plane, two are there. Okay. Is this clear till now? Is it clear till now? Okay. So I hope things are clear till now. Now my dear friends, till now you have seen that we are talking about so much stress, and you will be wondering that, sir, I have studied stress equal to force per unit area, F by A. Where is that formula? And now for the next 10 minutes, if you listen to me, you will get a very clear idea about the formula stress equal to force F by A. Very good evening, Raju. Okay. So what is the topic? Topic is average normal stress in axially loaded bar. Sir, I am double E student. Okay, Raju, not the entire syllabus. You know, due to time constraints, due to other commitments, complete syllabus doing on YouTube is not at all possible. That being said, time to time, we launch different series. And right now, the series that is going on is fundamental series. So what I will recommend, that try to attend the fundamental series of your, double E mentors, and you can ask them more about that when they are going to take the next classes. So definitely I will recommend that you attend the fundamental series. Okay, and time to time we launch different series. For example, in the month of September, problem solving series, gate booster series. So right now is the time of fundamental. Okay, but covering entire syllabus on YouTube is not possible, to be very honest. Okay. And for more, if you want to take the, in the description you will be finding some more details. Okay. My dear friends, I am talking about average normal stress in an axially loaded bar. Clearly you can see that along the axis, force is applied. Now, as I told that for stress, we have to go to the internal sections. External loadings are there, that is fine. But internally, what is the situation of the body, that we have to analyze. So let's say I have cut. I hope you can see this image. I am taking a plane. I am cutting at this section. Whatever I am taking, it is a section. Whatever I am taking, it's a section. So I hope you are able to see. This is the section that I am, drawing. And when I cut the body at this section, when I cut the body in this, in this way, so let's say I have separated. So suddenly, you know that there will be some internal force, And it is the distribution of that force that we are interested in. Now see, over here, so many little forces are coming, are getting generated. But one thing I know, that no matter how many small forces, many small forces will be there, but the resultant of that will be P. Because at that section, the net force is P. But many small, because every minute portion, means very small portion, even this minutest of portion of the body is resisting. So forces will be developed. That small forces developed is del F. And del F, you know that sigma, what did we studied about sigma? We studied about sigma as limit del F by del A when del A tends to 0. That means del A tends to 0. So very small area, and if I have to find the very small force, so you multiply with very small, area is there, so you multiply by stress, because stress is nothing but the quotient when del A tends to 0. Are you getting or not? Area is very small, and when I have to determine the small force, so you know that stress is there at the very minutest of area, that is the quotient, so you multiply by del A. So what I am trying to say, that if I have to find del F, there is sigma and you multiply by del A, just because we know that the quotient del F by del A is stress. Are you getting or not? Are you getting or not? Now see my dear friends, generally the body is continuous, and del, when the body is continuous, the body is complete. So this del F I can very easily write as dF, and this del A I can very easily write as dA. Yes or no? I can very easily write as dA. So dF is equal to sigma dA. And if I have to get the net internal force, if I have to get the total internal force, see, we are talking about internal forces, not external. Please, in this figure, when I am studying about stress, can you see external force? No. Here it is the P, and P is the net internal force. So if I have to get the total internal force, so dF hai, so I can very easily integrate na, because the body I have assumed to be a continuous. The body I am assumed to be continuous. And one more thing, I hope I'm sure you have forgot that. For before analyzing this, I have talked about prismatic bar. What is prismatic bar? Where the cross sections are same throughout. What is homogeneous? Homogeneous means the density is same throughout material. And what is isotropic? That the properties, whether it is physical and mechanical, they are same in all the directions. And that will be the assumptions. That means at least the homogeneous and isotropic will be the assumptions throughout your SOM subject. Before deriving any formula, you will definitely write homogeneous and isotropic. But this analysis, particular analysis, that is the average normal stress we are doing, this is, one thing is very important, this prismatic. We are talking about prismatic sections, prismatic bar. What is prismatic? What is prismatic? Prismatic is same cross sections. Whatever section you cut, the cross section will be same. Over here circular cross sections, bar mein to cylindrical, when you cut it will be circle cross sections. So when I am integrating, prismatic hai, homogeneous hai, so this will be, now what I have to know, that this sigma value will be constant. This sigma value will be constant. So integration of del F, so if you small internal forces, when you add all of them, the net internal forces will come na. I'll show the picture. Over here small forces you can see, and when you integrate all, one single P force will be there that you can see on the screen. So this resultant will be P, sigma is constant, I can take it out, and integration of dA will be A. And from here sigma is equal to P by A is coming into picture. I know everyone knows the formula sigma equal to P by A. But now if I ask you what is P and what is A, what will you tell? And for what, under what conditions this formula is applicable? This is another question. But first question is that sigma equal to P by A. Is P the external force? No. P is the net internal force. This formula is applicable for non-prismatic also? No. It is applicable for prismatic sections. Homogeneous, isotropic, all those assumptions are there. And what is sigma? What is sigma? Stress, not stress, average normal stress. If you simply say stress, that is no issue, but you must know that we are talking about average normal stress. So what is sigma? Average. Why average? Why average? Because you have found out for your entire section, for your entire area, you have Assume that there is one single average value of the stress, that's why you are saying average normal stress. Why normal? Because it is normal to the area, normal to the plane area. And what is P? P is the net internal loading, not external, internal. So then the formula of sigma equal to P by A comes into picture. So what is sigma? Sigma is the average normal stress at any point. What is P? P is the internal resultant force. Internal, not external, internal. So this is the formula, this is the way this formula have been developed. Obviously, if the force is in pulling, if the pull effect is there, so that force we say as tension, and if the push effect is there, so we say as the compression. Tension and compression. Right? So today we have, as I promised, today you got what are the highlights of this session? I'll show you. Just a minute. So today we started the session with the different types of loading, the different types of external loading. I've told you. Then I've told you that how linearly distributed load is being changed or is being analyzed, that I've told. We talked about the support reactions and how the reactions are being developed. What are the equations of equilibrium and how majority of our systems are coplanar in nature, and since it is coplanar we will be using only the 3 equations. Then I told you that in strength of materials external loadings will be there, but your focus should be on internal loadings, and that is why we have cut the section. You have cut the section, right? And when you have cut the section, I have talked about net resultant force, net resultant moment, and how I will draw 2 components, force ka bhi, moment ka bhi. One normal to, and second on the plane. So on the plane force, shear force, perpendicular, normal. Moment in the plane axis hai, bending. Axis agar perpendicular to the plane, torsion or twisting. And separate 4 different chapters we study in strength of materials. This is the force internal loadings that I am talking about. Then what is stress, how it is coming, all those things I have discussed. Then here I have tried to explain you the different directions. This is very important, my dear friends. Stress tensor or the stress 3D general state of stress at any point. जो state of stress है, the state of stress, how this one single cube is coming, that I have tried to explain. I hope it is clear. And then from that time we were thinking that when the formulas F by A will come, so that in the next 10 minutes I explained you that how the formula sigma equal to P by A comes. But now if someone asks you what is sigma, so you will not say stress. You, after seeing this session, you will say that sir, it is average normal stress. Average, why? I have told. Normal, why? I have told. Stress का मतलब already I have told in the beginning. What is P? Internal, net internal loading, not external, internal. See, equilibrium में तो internal will become external, that is different thing. Ultimately it is different thing, but okay, the original way is internal, and A is the area. And then average normal stress, all these things are fine, and then compression and tension. So today I have only talked about the concept of stress. tomorrow I'll be talking about average shear stress. The next topic that you can see over here is the concept of average shear stress. So from tomorrow I'll be talking about shear stress, and then I'll be talking about, after shear stress I'll be talking about strain. Strain will also come into picture, and similarly on different days I'll be talking about different concepts. For example, bending, torsion, SFD, PMD, stress transformation, all the critical concepts which are very fundamental to your understanding of SOM, I'll be talking 1 hour each day, that is 4 to 5. Right? Thank you, Amit. Thank you, Amit. I am obliged. Thank you. So, but mind it, my dear friends, this is not going to be a rigorous question solving series. As I said, I have to stick to the name of the series. The name of the series is Fundamental Series. That means I am going to strictly talk about the fundamentals. When the time will come, I will be talking about the questions also. We will be taking the questions or advanced concepts also. But in this series, my aim will be to build a very good fundamentals to the strength of materials subject that I am taking over here. Right? So with this, if you have any doubt related to the session, you can very neatly post it in the comment section. I will be addressing it myself personally. There is no issues with that. And please do come in the class regularly. If you have started watching, make sure that you watch all the 10 sessions that I am going to take on strength of materials. This will definitely boost your preparation as far as your 2025 GATE is concerned, and as a whole your basics will develop very good for this subject, that is strength of materials. So with this, my dear friends, I will be ending the session. I won't take much time. Thank you very much. God bless.